Hello, everyone. Welcome to lecture number 2 for the mini course on Einstein manifolds with symmetry for the third Geometric Analysis Festival. Let me briefly recall what this lecture will be about. So I want to be explaining the proof of theorem B presented in lecture 1. And theorem B says that given an Einstein manifold with negative Einstein constant, with a proper isometric action of a Lie group G, for which the orbit space is a closed manifold, then M can be foliated into minimal Einstein submanifolds of dimension of M plus 1. And there are many other conditions that are satisfied as well. And okay, so let me first focus on proving theorem B for the particular case of a Lie group G, which is as simple as it can be for the sake of this talk, right? So the first step for proving theorem B is to show that this last item 3 holds. Namely, we will show that the orthogonal distribution to the n orbits is integrable. And as I mentioned, we're going to be working exclusively with this particular Lie group G. So I call it G hyperbolic, not to be confused with the hyperbolic groups, sorry, but there's a very good reason why I call it like that. So the group G hyperbolic is a solvable, simply connected solvable Lie group given very explicitly by this set of matrices in GL S plus 1 of R, where A is a positive real number and V is a vector in R to the S. And it's neo-radical, it's S-dimensional, and it's given by this expression here. And an interesting feature is that this group acts simply transitively on hyperbolic space. Actually, I should have said of dimension S plus 1, not just any n. And by simply transitively, I mean that the isotropy subgroup is trivial. So it acts transitively and freely. And in fact, more is true. Any left invariant metric on this group is a hyperbolic metric, namely it has constant negative sectional curvature. So it's a very particular group, but for the sake of this talk, this will be enough to present many ideas involved in the proof of theorem B. Some other observations, well, the dimension is S plus 1, clearly. And another observation is that N is isomorphic as a Lie algebra to R to the S, namely N is abelian, as Lie group, sorry. N is an abelian Lie group, right? So one can write this algebraically by saying that the G hyperbolic is a semi-direct product of the positive real numbers times an abelian normal group of codimension 1. So we will work with this Lie group and assume that this group acts freely on your Einstein manifold M. So by that, I mean that if any element of the group fixes one point, then that element must be the identity. Right? So that ensures that the quotient is a smooth manifold. And we also assume, of course, that the quotient is not only a smooth manifold, but a compact smooth manifold, as in the theorem, right? Compact smooth manifold. Very ugly handwriting, but this is what Zoom gives me. I don't know why it looks all irregular. All right, so the setup that will be important for the proof of the theorem is that of the Riemannian submersions. So again, we have an Einstein manifold, which is invariant under an isometric and free action of this group G hyperbolic with compact orbit space, right? So the orbits of this group give a foliation of our manifold, right? And then turns out that there exists a unique metric on the orbit space B such that this projection is a Riemannian submersion, right? So what do I mean by that? What I mean is the following. So you look at the tangent space to M, right? And the tangent space to M has, at some point, it has a canonical subspace given by, is a vertical subspace given by the tangent space to the G orbit at that point, right? And then the orthogonal complement of that subspace is what we call the horizontal space, right? So of course the dimensions don't add up because this is one dimension and then B is two-dimensional in my picture, right? But just there's too many dimensions for me to draw a proper picture, just to give you an idea. So what do I mean by Riemannian submersion? What I mean is that I take G restricted to this horizontal subspace and I use the differential of pi to copy that to a metric on B. And the fact that G acts isometrically implies that this is well defined. Namely, if I take another point on the same orbit, then I'll get the same metric downstairs. So that's a Riemannian submersion. Essentially, the metric on B is determined by the metric upstairs by using the differential of pi. So this is like a dual concept of an isometric immersion, and it's particularly relevant for our purposes because, well, we have it, right? We have an isometric group action, and that gives rise to these very nice Riemannian submersions. So the notation that will be used is that vector fields which on M, right? Vector fields on M which are horizontal, namely they are orthogonal to the orbits of G, they will be denoted with letters X, Y, Z. And vertical vector fields, those which are tangent to the orbits, will be denoted by U, V, W, etc. This is Besse's notation for Riemannian submersions. And again, we have an orthogonal splitting, as I mentioned already, of the tangent bundle as this horizontal distribution and the vertical distribution. So we denote by G V for vertical the induced metric on the orbits. So notice that this is nothing but a family of left-invariant metrics on the Lie group G parameterized by the orbit space, because the action of G is by isometries, right? So there's a bunch of left-invariant metrics on G. And that's the extra missing piece of data that encodes what's going on with this, the geometry of these submersions is these two structured tensors defined by O'Neill. So the notation, the more standard notation for L is actually T, but we use a different notation because it's similar to the one used in the homogeneity one situation. That's the only reason. The O'Neill tensor A is a tensor that takes two horizontal vectors and maps and gives back a vertical vector field, and is defined as follows. I'm oversimplifying the presentation for the experts, so please do not complain. You can check all these in extreme detail and with full proofs and everything in O'Neill's original paper, or perhaps also in Besse's book, chapter 9, I guess. So the A tensor is defined by taking the Lie bracket of the two horizontal vector fields and then projecting onto the vertical component, right? So notice that A vanishes if and only if the horizontal distribution is integral. And then the L tensor is nothing but the second fundamental form of the orbits, right? So if you give a horizontal direction X, and then you just compute nabla X, where lambda is a Levi-Civita connection, evaluated at tangent directions. So this is by definition, the second fundamental form of the orbit say at the point P, right? Is the second fundamental form of the orbit GP in the direction of X. So these are very important elements of the submersion because, well, as I said already, A is 0 if and only if H is integrable. And L is 0, of course, even only if the g-orbits are totally geodesic, because it's the second fundamental form. And actually, both vanish simultaneously at every point, even only if M is locally a Riemannian product of B and some fiber. All right, so as a matter of fact, we will use another Riemannian submersion, not the one, so recall that we have M, G, it's Einstein, and it has an isometric action of this group G hyperbolic acting, right? But this group has a codimension 1 abelian subgroup N, which is an irradical, right? So we might look at the action of N, and this is actually what we have to do in order to obtain the result. And everything that I just said for the G action on M still applies for the N action on M. It's still a proper isometric action. The only difference is that now the quotient is not going to be compact. So we call this quotient P, right? So it's not compact, but it clearly admits an action of the quotient group G mod N, which is isomorphic to just the real numbers. So this acts on P, and the corresponding quotient is the original quotient of M plus G. So if you sit for a while and take a look at this diagram, it all makes perfect sense. So P is not compact, but the non-compactness comes from an isometric group actions, precisely the same that happens to M. And so this is the Riemannian submersion we will consider. And we call the corresponding quotient metric on P, GP. And then from now on, H and V will denote the horizontal and vertical subspaces for the submersion given by the action of N and not of G. Okay, so let me erase all this. So as I said already, P is non-compact, but the good thing is that there's still an isometric action of, in this case, a one-dimensional Lie group for which the quotient is isometric to a compact Riemannian manifold B. Now, notice that the good thing of our particular situation where N is abelian, because the orbits are, with induced geometry, are just left invariant metrics on N, then this implies that all the metrics G, V are flat. And this is very, very good news for us because it'll simplify the equations tremendously. So which equations, sorry to go back and forth, we have to study the Einstein equation, as I mentioned, in the context of a Riemannian submersion. So how do you do that? Well, you look at O'Neill's formula for the Ricci curvature in the context of a Riemannian submersion, right? So O'Neill's formula will give you 3 equations, namely a vertical one, a horizontal one, and then a mixed horizontal vertical one. I'm not writing the mixed one here because we're not going to use it, but the vertical equation and the horizontal equation coming from looking at this in the context of, you know, the Riemannian submersion, namely using this decomposition, are these 2 set of system of equations. So here, A and L, I've already explained what they are. These are O'Neill tensors, right? A is integrability tensor and L is the second fundamental form of the orbits. And N here, black N, not red N. Red N is a group. Black N is defined by this formula, and it's a mean curvature vector of the orbits. So it's a horizontal vector field. It's actually a basic vector field, namely it's invariant under the action of the group. and it's a mean curvature vector of the object. And then there are these terms, these traces, so to speak, like A star A and A star and L star L. These are positive, semi-definite bilinear forms defined in a very natural way. Just wrote it here for the sake of completeness, but not very important. Just, I think what's important is that this term, for instance, this term, right, is positive semi-definite. Right? This will be very important because for the estimates that come later on. And again, UI and XJ are local orthonormal frames, sorry. UI consists of vertical vector fields and XJ of horizontal vector fields. Okay, so as I mentioned, so in general, sorry, let me mention this briefly. There will be a term coming from the Ricci curvature of the fibers here. But this term does not appear in our case because, as I mentioned, the fibers with the induced metric are flat because N is abelian. So that simplifies a lot the situation that we have to consider. All right. Now, well, we have to work with this set of equations and try to obtain some information from them, right? The problem is that, I mean, you could think of this equation, right, is like an Einstein, let me call it Einstein-like equation for GB, but it's not quite the Einstein equation, right? Because there are a bunch of other terms. So maybe soliton, gradient soliton, if you want. Because of this term, which in some cases it will resemble the Hessian of some function. But it's not quite the gradient soliton equation for GB, right? There's more terms. And in this one, the observation is that this term here, which looks very complicated, this involves second derivatives of the matrix GV, right? Remember that the second fundamental form is by definition the derivative of the metric in the horizontal direction. So this is the derivative of the second fundamental form. So this is encoding second derivatives of the vertical metrics, right? And so in that sense, well, I mean, just it will be important for what's coming next, because we want to be looking at second order estimates for this, for certain geometric quantities. All right, so, well, we have to prove that the horizontal distribution is integrable. So in the language of Riemannian submersion, this amounts to saying that A equals 0. Okay. So what's the strategy for the proof? The strategy is to find a nice function f, which is G invariant. That's extremely important. The function is G invariant. Defined on M, it will induce a function on P. Recall that P is M mod N. So if it's G invariant in particular, it's also N invariant. So it gives rise to a function on P, which is still, you know, G mod N invariant. And it will satisfy the following estimate. So the Laplacian f plus some first order term has a sign. So here y is some vector field on P. And the important thing is that equality in this estimate will imply a bunch of rigidity conditions, in particular the fact that O'Neill's A tensor is 0, and many other interesting things as well. Right? So this is a strategy. Try to find a function which satisfies this differential inequality or something like that. So why this is a reasonable strategy? Well, the corresponding function on B, right? Because F is G invariant, it induces a function on the quotient of M by G, which is compact smooth manifold. And one will obtain an estimate of the form Laplacian F tilde plus first order term is non-negative, right? But then by the maximum principle, equality must hold everywhere on M. Because if you apply the strong maximum principle, right, this cannot happen unless F tilde is constant. And here it's extremely important that when we apply this global argument, that B is compact. And so in order to reduce to the compact quotient B, it was crucial that F was G invariant and not only N invariant. We are looking at the N submersion, but we need a G invariant function to use compactness. All right, so then equality holds everywhere, and then our rigidity holds everywhere. And in particular, this proves the first step, and it will give us also a bunch of other geometric conditions that are non-trivial, and that will help for proving the Alekseesvskii conjecture later on. So that's the strategy. I hope it's clear. So where will this F be coming from, right? Or this F, sorry, where will it come from? Well, there's a recent work on the Einstein equation with symmetries. And from this, one can see that a good candidate is to look at what's called the relative volume of the N orbits. Okay. So this work by Neighbor and Tian and by John Lott. They both, in both papers, they use the relative volume of the orbits to obtain a similar differential inequality, that the one we're looking for. So what's the relative volume of the orbits? Well, imagine for a minute, imagine that the orbits will be compact, right? They are not, because N is not compact. Well, then you can compute the volume, and then the gradient of the logarithm of the volume is related to the mean curvature vector. Right? But this holds actually in general. So if you look at the mean curvature vector of the orbits, then it can be proved that this is a gradient vector field on M. And it's a gradient of a function which we call logarithm of Vn, inspired by what I just mentioned, minus logarithm of Vn. And this Vn is some N invariant function on M. So this actually works in the case that's considered in this paper. But for us, unfortunately, it won't be enough, because I made emphasis in the previous slide that the function we're looking for has to be G invariant. And the problem with the relative volume of these N orbits is that, I mean, there's a very explicit expression for V. I mean, this sounds very mysterious, right? But one can look at just a bunch of left invariant frame, vertical left invariant frame, and then look at the metric coefficients in this frame, and then consider Vn to be somehow the determinant of Gij. Perhaps there's a 1/2, I don't remember, but one can compute it explicitly, right? So it's easy to see that this is an N invariant function and that its gradient is related to the mean curvature vector. Now, the problem with this relative volume is that it is not G invariant. Essentially, because the group G is not unimodular. That means that if you look at the G orbit, right, G orbit, there's the N orbits right, which are of codimension 1 in in the G orbit. And the problem is that even though Vn is invariant along each n orbit, right? When I move around and I come back here, right? The relative volume will change because the action defining the semi-direct product, remember this is n, this action of R on Rs is not by matrices of determinant 1. So that will change the determinant of my metric. And that means that essentially what I mentioned, right? The Vn is not G invariant. So it cannot be used for our purposes because we won't be able to apply any maximum principle, essentially because P, remember P, M mod N, is non-compact, right? So no maximum principle there. No integration. If you want to use the diversion theorem, some other arguments, nothing will work. Nothing. There are counterexamples to any such statements. So how to overcome that? Well, the idea is, okay, we look for a G invariant V, which somehow satisfies a similar equation. Namely, try to write N as minus gradient log V plus N naught. Now, V is a G invariant function and N naught is to be determined. So what is natural for us to take? In fact, it turns out that the natural thing to consider is a modified version of the Helmholtz decomposition. So recall that Helmholtz decomposition is just very classical way of decomposing any vector field as a sum of a gradient vector field and a divergence-free vector field. So you can always do this on a compact Riemannian manifold, say, essentially by solving Poisson's equation. But we gonna be needing a modified version of this decomposition, which holds thanks to the following proposition. On a compact manifold, the second order linear elliptic PDE divergence of gradient u plus ux for any vector field x on the manifold admits a unique up to scaling positive smooth solution. Positive, I mean, well, u is positive everywhere. So this is true. We had to prove it because we couldn't find the reference, and we asked many people, and luckily some people were nice enough to share the ingredients of a proof. But it seems like a very standard result, but we don't have a reference. So if you know a good reference for this, please feel free to share it with me. So as a corollary, we get immediately the existence of a decomposition which satisfies the following. So for any vector field on B, there exists a positive function V and another vector field x naught, which satisfies the following equation, the one we wanted for N. And now x naught is not divergence free, but V times x naught is divergence free. This sounds strange, but and we would like to understand geometrically what this means, but it turns out that this is what the equations ask for. How do you prove such the corollary from the proposition? Well, you essentially said, I mean, if you have this V solving this equation, right? Then you set x naught, sorry. I guess you can write this as V times gradient log V plus X. And then you set X naught to be this. and you get your decomposition. All right. Now this all works on a compact Riemannian manifold B. There's an equivariant version on P, and remember that P has a group action which keeps P as orbit space. And then applying the equivariant version of this decomposition to the mean curvature vector n of the n orbits in M gives a function V, which is G invariant, not only n invariant, but G invariant, and which satisfies these two conditions. Okay. Now, to make a long story short, it turns out that if you consider F to be the logarithm of this function V, and you need to add a correction term, which involves the norm squared of this remaining part of the mean curvature vector, which is not quite the divergence-free part, but what it's defined up there, right? Recall that this is there's a unique such decomposition, right? So this is all well defined. Then this function f, right? It's a function, it's a G invariant function on M, and it satisfies the following estimate: Laplacian f on P plus the gradient of log B plus n naught, scalar product with nabla f, is greater than or equal to 0. Right? Remember that we don't care about the first order term, which is just some vector field here. And it was precisely what we were looking for, right? So because it is G invariant, this will give rise to a similar equation on B, which is compact. And then by applying the maximum principle, we can deduce that equality holds everywhere. And then of course, the way we obtain this estimate is by using the Einstein equations that I wrote in the previous slides, right? And so in particular, at some point you have to throw away this term A star A, right? And of course, for equality to hold, well, A has to be 0. And many other things will happen as well. So this is essentially the idea for proving theorem B in this particular case. Okay, sorry. This is first step, right? We only know that, but once you have the first estimate, then life is much easier. So we showed that the orthogonal distribution to the n orbits is integrable. We still haven't quite obtained this foliation by minimal Einstein submanifolds, but once we know so much, then I claim that this is just a computation. So you just consider the n orbits, right? In M, n orbits. And then look at the mean curvature vector of these n orbits, right? The distribution spanned by this is of course of dimension n plus 1, will be integrable. And the integral submanifolds are going to be the Einstein minimal submanifolds that we were looking for. Okay, and essentially one can compute the Ricci curvature because we know so much already, and there's nothing else in this case that has to be done. Right? So this concludes the idea of the proof for theorem B. All right, so this is the end of lecture 2. In lecture 3, we will apply theorem B to prove the Alekseesvskii conjecture. So I hope you're still with me and that you ask many questions about things that might not be as clear as I intended to. And yeah, this is the end of lecture 2. See you in the next one.